100,000 years. That is how long the Earth waits before it freezes again. Not metaphorically, not symbolically, physically. Ice rises where forests once stood. Oceans retreat from their shores. Entire regions vanish beneath a white silence that lasts longer than all of recorded human history combined. It has happened repeatedly, long before cities, long before agriculture, long before memory itself. At the height of the last ice age, nearly a third of the northern hemisphere lay buried under ice sheets up to 2 miles thick. New York would have been erased. Chicago would not exist. London would sit beneath a frozen desert stretching toward the horizon. Sea levels were more than 120 meters lower than today. Coastlines pushed hundreds of miles out. Land bridges connected continents that are now separated by oceans. Humans crossed into North America on foot. They moved into Australia across exposed shelves of land. The map of the world was different. And yet this was not an anomaly. It was part of a rhythm. For the past 2.6 million years, Earth has oscillated between long glacial periods and shorter, warm intervals. The frozen phases dominate the timeline. Warm periods, like the one we live in now, are brief interruptions. If the last million years were compressed into a single calendar year, most of it would be winter. The strange part is the timing. Roughly every 100,000 years, global ice volume builds slowly, peaks, and then collapses back into warmth. The regularity is too structured to be random. It resembles a pulse, a planetary heartbeat operating on timescales so slow that no human civilization has ever experienced a full cycle. Imagine standing at the southern edge of the Laurentide ice sheet 20,000 years ago. Before you stretches a wall of ice taller than skyscrapers, grinding forward inch by inch. It crushes forests, reroutes rivers, and presses the Earth's crust downward under its weight. When the ice eventually melts, the land rebounds upward over thousands of years. The ground itself breathes in response to the freeze. And yet, this frozen world eventually thawed. Temperatures rose. The ice retreated north. Meltwater flooded valleys and carved vast channels across continents. Sea levels climbed. Forests expanded. Humans who had survived in scattered populations during the cold peak began clustering in warmer, more stable regions. Agriculture emerged. Settlements formed. Civilization began. All within a narrow, warm window that, in geological terms, is unusually calm. Here is the tension. The astronomical changes that influence Earth's climate are subtle. The tilt of the planet shifts slightly. Its orbit becomes marginally more elliptical or more circular. Its axis wobbles over thousands of years. These variations alter how sunlight is distributed across seasons and latitudes. But the total change in energy is small, only a few percent. A few percent should not be enough to bury continents under ice. A few percent should not be enough to lower sea levels by more than 100 meters. And yet that is exactly what happens. So we arrive at the central question that will follow us through this entire journey. If the trigger is small, why is the freeze so vast? Why does a subtle shift in sunlight eventually create glaciers capable of reshaping continents? The answer cannot lie in sunlight alone. Something within the Earth system must amplify the signal. A feedback, a cascade, a threshold that, once crossed, locks the planet into a different state. Ice ages are not accidents. They are not random catastrophes. They are phases of a system that has been operating long before us and will continue long after us. The clock is real. The pulse is measurable. The evidence is carved into rock, sealed in ice, and layered across the ocean floor. We are living in a warm pause between freezes, and the clock is still turning. If the freeze were a single event buried in deep time, it might feel distant. but the pattern repeats. Ice advances, ice retreats. The timing is structured enough to measure. The planet does not stumble into glaciation. It moves there slowly, almost methodically. The first shift is subtle. Northern summers become just slightly cooler. Snow that once melted completely now lingers a little longer. That lingering snow reflects sunlight back into space. Reflection reduces heat absorption. Reduced heat allows more snow to survive the following summer. Over centuries, the imbalance grows. Snow compacts into ice. Ice thickens. Thick ice spreads. As it spreads, it brightens the surface of the planet, bouncing even more sunlight away. Cooling deepens. What began as a minor seasonal adjustment becomes a reinforcing cycle. But ice alone does not build continents of frozen mass. The oceans begin to respond. Cold water holds more carbon dioxide than warm water. As oceans cool, they draw CO2 from the atmosphere. With less carbon dioxide overhead, the greenhouse effect weakens. Heat escapes more easily into space. Temperatures drop further. Colder oceans absorb even more CO2. The feedback tightens. A small orbital variation has now become a planetary cascade. Ice ages do not arrive overnight. They build over tens of thousands of years. Ice sheets thicken until they are capable of altering atmospheric circulation. They redirect winds. They reshape storm tracks. They create their own regional climates. Their weight presses the crust downward. Even today, parts of Canada and Scandinavia are still rising from the load of ice that melted thousands of years ago. The planet remembers the freeze in its very shape. And yet, the return to warmth can be abrupt. Ice sheets that took tens of millennia to grow can collapse far more quickly. Carbon dioxide rises, temperatures surge. Within a few thousand years, the white shield withdraws north. Rivers flood with meltwater. Sea levels climb. Forests reclaim land that had been tundra. Why does the descent into cold stretch across vast spans of time, while the escape from it can happen faster? The imbalance hints at thresholds. The system accumulates pressure slowly. Once a boundary is crossed, release can be rapid. The climate does not glide gently between states. It shifts once conditions align. And still, the deeper puzzle remains untouched. The astronomical changes that initiate these shifts are modest. Variations in Earth's orbit alter sunlight distribution by small margins. The total energy difference is not extreme. Nothing in the mathematics of orbital mechanics screams continental ice, yet continents freeze. This suggests amplification inside the Earth system, feedback layered upon feedback. Ice reflects light. Oceans absorb carbon. Carbon alters temperature. Temperature alters circulation. Circulation alters precipitation. Each component reinforces the others once the direction is set. But here is the tension that makes the mystery sharper. Around 1 million years ago, the pacing of ice ages shifted. Earlier cycles followed a 41,000-year rhythm linked closely to changes in Earth's tilt. Then the dominant beat became 100,000 years, aligned with a weaker orbital variation. The faintest astronomical rhythm became the strongest climate signal. Why would the weakest beat control the dance? Ice sheets may have grown thicker over time, becoming harder to melt and slower to respond. Ocean circulation may have reorganized, changing how heat and carbon move through the planet. Invisible thresholds may have been crossed. Yet no single explanation closes the case. What is clear is this: the freeze is not random. It is systemic, a convergence of subtle forcing and powerful feedback, and we are living in the calm between convergences. The Holocene, our current warm interval, has been unusually stable. Temperatures have fluctuated within a narrow band. Sea levels have held steady for millennia. Rainfall patterns have been predictable enough to support agriculture and cities. Every structure humanity has built rests on that stability. But stability, in geological terms, is temporary. Orbital cycles continue. The tilt shifts, the wobble progresses. The orbit stretches and relaxes. The clock does not pause simply because we exist. Which brings us back, quietly but firmly, to the question that will not go away. If the trigger is small, why is the freeze so vast? The answer lies somewhere in the amplification, in the hidden machinery of ice, ocean, and atmosphere acting together across deep time. The pulse continues, and we are between beats. In the early 19th century, the idea of a global ice age sounded absurd. Europe was emerging from centuries of theological explanations for natural phenomena. Geological time itself was still controversial. The prevailing belief was that landscapes were shaped either by slow, uniform processes or by a single catastrophic flood described in Scripture. Then came the boulders. Across northern Europe and North America, enormous rocks sat in places where they clearly did not belong. Granite blocks rested on limestone plains. Massive stones lay scattered far from any mountain range that could have produced them. Some were the size of houses. At first, scientists proposed floods. Perhaps torrents of water had carried them there. But water leaves certain signatures. Erosion patterns, sorted sediments, channels consistent with flow. These boulders did not fit that explanation. Then came the scratches. Across bedrock in Scotland, Switzerland, Scandinavia, and later North America, long parallel grooves were discovered carved directly into stone. They ran in consistent directions across vast distances. The markings looked deliberate, almost engineered. Water does not carve stone in straight parallel lines across continents. Ice does. In 1837, a Swiss naturalist named Louis Agassiz proposed something radical. Much of Europe had once been buried beneath a massive ice sheet. Not mountain glaciers, not regional frost, continental ice. His colleagues laughed. The idea seemed extreme. A frozen Europe? Ice covering Germany, France, Britain. It felt apocalyptic. It felt implausible. But evidence kept accumulating. Moraines, ridges of debris left behind by glaciers, appeared far beyond modern glacial boundaries. U-shaped valleys, characteristic of glacial erosion, stretched across landscapes now temperate and green. Lakes filled basins carved by slow, grinding ice. The more geologists looked, the more the pattern emerged. Ice had once advanced far beyond its present limits, and not just once. As studies expanded into North America, the scale became undeniable. The Great Lakes were not simply depressions filled with water. They were gouged by enormous glaciers. The soil composition of the Midwest bore the signature of glacial till, unsorted sediment dropped directly by melting ice. The flood hypothesis collapsed. By the late 1800s, the scientific community could no longer dismiss the evidence. The Earth had experienced an ice age. In fact, multiple ice ages. This realization altered humanity's understanding of climate forever. The planet was not climatically static. It had swung between radically different states, and those states were not ancient in the way dinosaurs were ancient. The last major glaciation had ended only about 11,700 years ago, within the time span of human existence. But discovering that ice ages occurred did not explain why. The 19th century could describe the scars. It could map the debris. It could reconstruct the extent of the ice. What it could not do was explain the rhythm. Why would a planet freeze and thaw repeatedly? Volcanoes were proposed. Mountain building was suggested. Changes in ocean currents were debated. Some even speculated about variations in the sun's energy output. Yet none of these ideas accounted for the structured timing that slowly emerged from the data. Because as geological methods improved, scientists began realizing something extraordinary. Glaciation was not random. It appeared cyclical. The idea of cycles raised a deeper tension. If climate swings followed a rhythm, then the cause might not be internal alone. It might lie in something external, something astronomical. But before that hypothesis could be tested, the timeline itself had to be established, and that required a new kind of evidence, one that did not merely sit on the surface of the Earth but was locked deep within it. Ice remembers. Ocean floors remember. And those memories would eventually reveal that the freeze was not a singular event, but a repeating pulse stretching back hundreds of thousands of years. Still, at this stage in history, the mystery remained intact. The planet had frozen. The scars were everywhere. But the engine behind the freeze was invisible, and the central question sharpened. If the freeze is real and vast, what mechanism could be powerful enough to produce it, yet subtle enough to repeat with rhythm? The answer would not come from the surface. It would come from drilling deep into time itself. The surface of the Earth tells a dramatic story, but it is incomplete. Glacial scars reveal that ice once advanced. Moraines and boulders confirm its reach. Yet surface evidence cannot measure timing with precision. It cannot reveal atmospheric composition. It cannot tell us how cold it was or how quickly temperatures shifted. To uncover that, scientists had to go deeper. In the mid-20th century, a new frontier opened, not across continents, but beneath them. Researchers began drilling into the Greenland and Antarctic ice sheets, extracting long cylindrical cores of compacted snow and ice. Each layer represented a year of snowfall, compressed and preserved. Trapped within the ice were tiny bubbles of ancient air, sealed samples of past atmospheres. For the first time, scientists could directly measure carbon dioxide levels from tens of thousands, then hundreds of thousands of years ago. They could reconstruct temperature variations from isotopic signatures within the ice itself. What they found was not chaos. It was rhythm. Carbon dioxide rose and fell in sync with temperature. Cold periods aligned with low CO2. Warm intervals aligned with higher concentrations. The pattern repeated over and over, stretching back hundreds of thousands of years. As drilling techniques improved, ice cores reached deeper, revealing nearly 800,000 years of climate history. And the cycles were unmistakable. Cold, warm. Cold, warm. Roughly every 100,000 years. Ocean sediments told the same story. Microscopic marine organisms sensitive to water temperature left chemical signatures in their shells. As these organisms died and settled on the ocean floor, they formed layered archives of past climates. By analyzing oxygen isotopes in these sediments, scientists reconstructed global ice volume over millions of years. The signal matched the ice cores. The freeze was not a single event. It was a repeating system. This discovery changed the question entirely. The debate was no longer about whether ice ages existed. It was about what paced them. The timing was too structured to be random volcanic activity, too regular to be explained by sporadic mountain building. Solar output variations alone could not account for the consistency. The cycles hinted at something astronomical, something tied to Earth's motion through space. In the early 20th century, a Serbian mathematician named Milutin Milankovic calculated how variations in Earth's orbit might alter the distribution of sunlight across the planet. He proposed that changes in orbital eccentricity, axial tilt, and precession, slow, predictable shifts, could influence long-term climate. At the time, the theory was elegant but unproven. There was no detailed climate record to compare it against. Decades later, the ice cores and ocean sediments provided exactly that. When researchers overlaid Milankovic's orbital calculations with the geological record, the correlation was striking. Peaks and troughs in ice volume aligned with variations in Earth's orbital geometry. But alignment did not equal explanation. Orbital cycles alter sunlight distribution modestly. They do not drastically change the total energy reaching Earth. The variations are subtle, measured in small differences of seasonal insolation, particularly at high latitudes. And yet those small shifts corresponded with the growth of massive ice sheets. The evidence was now clear. Ice ages were paced by orbital mechanics. But pacing is not the same as power. The orbit might set the tempo, but something else amplified the effect. The climate system was responding disproportionately to minor changes in sunlight. The feedbacks were enormous. Ice sheets kilometers thick, sea levels dropping over 100 meters, global temperature swings of 5 to 6 degrees Celsius. The mechanism was not linear. The more the data accumulated, the clearer it became that the freeze was a product of interaction, orbital forcing combined with internal feedbacks. Still, the shift from 41,000-year cycles to dominant 100,000-year rhythms remained unresolved. The strongest correlation early in the record matched axial tilt. Later, the weaker eccentricity cycle dominated. The astronomical signal had not grown stronger. The climate response had changed. Why would the Earth system become more sensitive to a weaker beat? The ice cores could show us timing. The sediments could confirm scale, but neither could fully explain the transition, which returns us, again, to the central thread. If the orbital trigger is small, why is the freeze so vast? And why did the system eventually synchronize with the faintest astronomical rhythm? The evidence is layered. The pattern is undeniable. The scars are carved into continents and sealed in ice. The freeze is real. The rhythm is real. The amplification is real. But the full machinery behind it remains partially hidden, operating slowly, quietly across spans of time far beyond human intuition. And the clock continues to turn. By the time orbital cycles were confirmed as the pacing mechanism behind ice ages, the explanation seemed almost elegant. Earth's orbit shifts slightly. Sunlight distribution changes. Ice grows or melts accordingly. The system pulses. But the ice cores told a more complicated story. When scientists drilled deep into Greenland, they expected to see slow transitions, gradual cooling, gradual warming. Instead, they found abrupt jumps. Temperatures in the North Atlantic region sometimes rose by several degrees within decades. Then, they fell again. The glacial world flickered. These events, known as Dansgaard-Oeschger oscillations, revealed something unsettling. Ice ages were not stable, frozen plateaus. They were tense states, prone to sudden shifts. Orbital changes unfold over tens of thousands of years. These temperature jumps happened in lifetimes. Something inside the climate system was capable of amplifying slow forcing into rapid change. The focus turned to the oceans. Beneath the North Atlantic lies a massive circulation system that transports heat from the tropics toward higher latitudes. Warm surface water flows north, releases heat, cools, sinks, and returns south at depth. This overturning circulation moves enormous amounts of energy. Disrupt it, and regional climate shifts dramatically. During glacial periods, vast ice sheets periodically released fleets of icebergs into the ocean. These Heinrich events flooded the North Atlantic with fresh water. Fresh water is lighter than salt water. Too much of it can slow the sinking of cold, dense water, the engine of the circulation. Slow the engine, and heat transport weakens. Weak heat transport means colder northern regions. The result was instability layered on top of long-term cooling. This discovery reshaped how scientists understood glaciation. Orbital forcing might set the stage, but internal feedbacks determine how the system behaves moment to moment. The Ice Age was not just a slow descent into cold. It was a dynamic state balancing on thresholds. And thresholds matter. Imagine a system accumulating stress slowly. Ice builds year after year. CO2 declines gradually. Ocean circulation adjusts incrementally. For thousands of years, the change appears smooth. Then a tipping point is reached. Circulation reorganizes. Temperature shifts abruptly. The system snaps into a new configuration. The descent into glaciation is slow because the buildup of ice takes time. But once feedbacks align in the opposite direction, when insulation strengthens, when CO2 rises, when ocean heat transport intensifies, deglaciation can proceed more rapidly. This asymmetry hints at something non-linear. The climate does not move like a pendulum swinging evenly between two extremes. It behaves more like a system that resists change until resistance collapses. But an even deeper puzzle remains. Early in the Quaternary period, glacial cycles followed a 41,000-year rhythm tied closely to changes in Earth's axial tilt. Later, around 1 million years ago, the dominant pacing shifted to roughly 100,000 years, corresponding to eccentricity, the weakest orbital variation. The astronomical input did not dramatically strengthen, yet the climate response reorganized. Why would the system begin favoring a weaker beat? One possibility is inertia. As ice sheets grew larger over successive cycles, they became more stable and slower to melt. Larger ice masses might require longer forcing intervals to collapse, aligning more naturally with the 100,000-year cycle. Another possibility lies in the oceans. Deep ocean circulation integrates heat over long timescales. If ocean dynamics began filtering out shorter cycles, emphasizing longer ones, the system could lock into a slower rhythm. But no single explanation fully resolves the shift. What is clear is that orbital forcing alone cannot explain magnitude. It provides timing. It does not provide scale. The scale comes from feedback. Ice reflects sunlight. Cooling oceans absorb carbon dioxide. Lower CO2 weakens the greenhouse effect. Colder temperatures allow ice to grow further. Each element reinforces the others once the direction is set. Which brings us back, quietly, persistently, to the central question. If the trigger is small, why is the freeze so vast? Because the system amplifies. Because thresholds exist. Because once ice, ocean, and atmosphere synchronize, subtle nudges become continental transformations. The clock ticks gently. The response can be enormous. And that imbalance is the heart of the mystery. If amplification is the key, then we have to look closely at the mechanisms that magnify weak orbital shifts into continental ice sheets. The most powerful of these mechanisms begins with something deceptively simple: brightness. Ice is bright. Fresh snow can reflect up to 80 to 90% of incoming sunlight. Dark ocean water reflects far less. Forests absorb more still. When ice expands, the planet becomes more reflective. More reflection means less absorbed energy. Less absorbed energy means cooling. Cooling allows more ice to persist. This is the ice albedo feedback, and it is one of the strongest amplifiers in the climate system. At first, a slight decrease in summer sunlight at high latitudes allows snow to linger. Lingering snow becomes compacted ice. Ice spreads outward. As it spreads, the surface of the Earth brightens. More sunlight is deflected back into space. Cooling accelerates. The feedback does not require dramatic forcing. It requires persistence. But ice albedo is only the beginning. As ice sheets expand, they alter atmospheric circulation. Large ice masses act like topographic features. They redirect wind patterns. Storm tracks shift southward. Dry air expands over regions that were once temperate. Dust increases in the atmosphere carried from exposed glacial outwash plains. Dust affects climate in two ways. It can reflect sunlight, reinforcing cooling, but it also carries iron into the oceans. Iron fertilizes phytoplankton growth. Increased phytoplankton absorb more carbon dioxide through photosynthesis. When they die, some of that carbon sinks into deep water. Lower atmospheric CO2 weakens the greenhouse effect, and once again, the system cools further. Then, There is the ocean itself. The ocean stores vastly more heat than the atmosphere. It integrates energy changes over long timescales. During cooling phases, the deep ocean gradually loses heat. As it cools, its capacity to absorb carbon dioxide increases. More CO2 leaves the atmosphere and dissolves into seawater. The greenhouse blanket thins. This is not a single feedback. It is a network. Ice reflects. Oceans absorb carbon. Carbon alters temperature. Temperature alters circulation. Circulation influences precipitation. Precipitation affects ice growth. The system is layered, and each layer reinforces the others once movement begins in a particular direction. But feedbacks also create resistance. When warming begins, the reverse processes must unfold. Ice retreats, reducing reflectivity. Darker surfaces absorb more sunlight, accelerating melt. CO2 rises from warming oceans, strengthening the greenhouse effect. Heat builds faster than before. This helps explain why deglaciation can proceed more rapidly than glaciation. The collapse of feedbacks can be swift once thresholds are crossed. Yet even with amplification understood, the 100,000-year dominance remains puzzling. Eccentricity, the slight stretching and relaxing of Earth's orbit, produces relatively weak changes in sunlight. On its own, it should not dominate. But eccentricity modulates the strength of precession, influencing how sunlight is distributed seasonally across hemispheres. Perhaps eccentricity acts as a pacing envelope, not strong by itself, but capable of synchronizing other cycles. When ice sheets grow large enough, they may become sensitive only to stronger alignments in seasonal forcing, which occur at 100,000-year intervals. In this view, the climate system is not simply reacting to one cycle, it is integrating multiple ones. Tilt, precession, eccentricity, interacting through feedback loops that evolve over time. And that evolution matters. Over millions of years, atmospheric carbon dioxide gradually declined due to tectonic processes, mountain building, and chemical weathering. As baseline CO2 fell, the planet became more prone to glaciation. Once large ice sheets formed, they altered global dynamics permanently. The climate system crossed into a regime where long, dominant glacial cycles became possible. In other words, the amplification itself evolved. The machinery that produces massive ice sheets today may not have operated the same way 3 million years ago. The system reorganized as background conditions shifted. But even this deeper context does not eliminate the core tension. The orbital trigger remains modest. The freeze remains vast, which suggests that magnitude is not solely about forcing strength. It is about sensitivity. A system can respond disproportionately when it sits near thresholds. The closer it is to tipping, the less push it requires. Ice ages may be less about overwhelming external change and more about a climate system balanced near instability. And that idea carries implications. Because if the system can amplify small cooling nudges into glacial maxima, it can also amplify warming nudges. Feedback does not choose direction. It magnifies whatever trend begins to dominate. For nearly 1 million years, the Earth has oscillated within this amplified rhythm. Cold dominates most of the timeline. Warm intervals interrupt. Ice builds slowly. Ice collapses faster. And through it all, the orbital clock continues. Quiet, predictable, relentless. But the amplification, the real engine of magnitude, lies within the planet itself. And that engine is still running. If ice ages are built on amplification, then survival during them is not theoretical. It is immediate. When the freeze deepens, it does not announce itself with a single catastrophic moment. It advances gradually, season by season, year by year, generation by generation. Imagine living 25,000 years ago in Northern Europe. Summers are short and cool. Winters are long and punishing. The growing season shrinks. Herd animals migrate unpredictably. Rivers freeze longer each year. What begins as subtle cooling eventually transforms the landscape into steppe and tundra. Agriculture does not exist. Stability does not exist. Survival depends on mobility. As ice sheets expand southward, ecosystems reorganize. Forests retreat. Grasslands widen. Dust fills the air from exposed glacial plains. The world becomes drier. Water is locked inside continental ice sheets. Sea levels fall dramatically. Shorelines stretch outward. Entire coastal plains emerge where oceans once stood. Humans adapt or vanish. During glacial peaks, populations fragment into refugia, pockets of habitable land shielded from the harshest cold. Southern Europe, parts of the Near East, segments of East Asia. These regions become lifeboats of biodiversity and human survival. Genetic evidence suggests that many human lineages bottlenecked during these cold intervals. Populations shrank. Some disappeared entirely. Neanderthals, who endured multiple glacial cycles, eventually vanished during a period of severe climatic instability. Climate pressure does not simply challenge survival. It shapes evolution. Large mammals adapted to the cold. Mammoths with thick fur and curved tusks. Woolly rhinoceroses, steppe bison. But even these giants were not immune to rapid shifts. When warming came abruptly, habitats changed faster than species could adjust. The freeze was not only about temperature, it was about water distribution. With sea levels more than 120 meters lower, land bridges connected continents. Humans crossed from Siberia into North America across Beringia. Southeast Asia connected to land masses now separated by ocean. Migration routes opened, then closed again when the ice retreated. Geography itself pulsed with the climate. And yet, life persisted. This is the quiet resilience of the glacial world. Despite vast ice sheets and harsh conditions, ecosystems stabilized within the cold regime. Grasslands thrived in some regions. Cold-adapted species flourished. Humans developed technologies, tailored clothing, controlled fire, cooperative hunting, that allowed survival in extreme climates. But stability within the freeze was fragile. Abrupt warming events could destabilize food chains. Sudden cold returns could devastate migrating herds. The glacial world balanced on thresholds, just as the climate system did. And here again, the central question hovers. If the trigger is small, why is the freeze so vast? Because once ice expands far enough, it reshapes everything. It alters wind patterns, redirects rainfall, locks away fresh water, lowers sea level, and reorganizes ecosystems. The feedback is not confined to temperature alone. It permeates the entire planetary system. The Ice Age becomes the dominant state, not because the sun dims dramatically, but because the Earth responds collectively. Ice sheets grind landscapes flat. They carve lakes. They leave behind fertile soils in some regions and barren rock in others. When they retreat, they do not restore the previous world. They reveal a transformed one. We often imagine ice ages as static winters lasting thousands of years, but they are dynamic, pulsing, unstable, capable of sudden shifts, and through all of it, the orbital rhythm continues in the background, steady, predictable, indifferent. The freeze advances slowly, survival adapts, the planet reorganizes, and the amplification persists. But survival inside a glacial world is not only about enduring cold. It is about enduring unpredictability. During the last ice age, climate did not move in a smooth line from cold to colder. It flickered. Greenland ice cores reveal temperature jumps of up to 8 degrees Celsius within decades. Imagine living through that. A generation born into bitter cold could witness sudden warming within their lifetime. Rivers thawing earlier, vegetation shifting north, only to see conditions reverse again. For hunter-gatherer societies, this volatility was existential. Animal migrations depended on plant growth. Plant growth depended on temperature and rainfall. If warming came abruptly, grazing patterns shifted, herd routes changed. If cooling returned, newly established food sources disappeared. The margin for error was thin. Ice sheets themselves were not static walls. They surged, they fractured, they released torrents of meltwater during warmer pulses. Vast proglacial lakes formed at their edges. When ice dams failed, floods of unimaginable scale swept across continents, carving channels hundreds of kilometers long. These were not gradual transformations. They were system-wide responses triggered once thresholds were crossed. And the thresholds mattered. As ice accumulated over tens of thousands of years, it depressed the crust beneath it. Entire regions sank under the weight. This altered drainage patterns. Rivers reversed direction. Lakes formed in new basins. When deglaciation began, meltwater poured into oceans, raising sea levels rapidly. Coastal settlements, had they existed, would have vanished beneath rising tides. Sea level rise after the last glacial maximum was not smooth either. There were pulses, episodes where oceans rose several meters within centuries. Shorelines shifted inland. Habitable land shrank. The freeze, then, was not only about expansion of ice. It was about the redistribution of water. Water locked in glaciers dries out continents. Deserts expand. Rain belts migrate. Monsoons weaken or intensify depending on circulation shifts. Regions that are fertile today could become arid under prolonged cooling. The glacial world reorganizes climate zones globally. And yet, amid all this pressure, human beings adapted. Archaeological evidence shows sophisticated tool-making during glacial periods. Complex social networks likely emerged to buffer against local shortages. Trade routes connected distant groups, sharing resources and information. Cooperation became survival strategy. Cold may have limited agriculture, but it did not halt innovation. Still, the stability required for dense urban civilization never existed within the glacial regime. Long-term farming depends on predictable seasons. Cities depend on stable coastlines and consistent water sources. Ice ages undermine predictability. Which raises an uncomfortable thought. Our entire global infrastructure, agriculture, ports, megacities, depends on Holocene stability. We have never tested civilization against a slow return to glaciation. If orbital cycles continued undisturbed, cooling would eventually begin again. It would not freeze continents overnight. It would creep southward over millennia, but the effects would accumulate. Shorter growing seasons, expanding snow cover, shifting rainfall belts. And because feedback amplifies small changes, the descent would not remain small forever. Yet we are not passive observers. Atmospheric carbon dioxide now exceeds levels seen in at least 800,000 years of ice core data. The rise has been rapid, compressed into centuries rather than millennia. If falling CO2 helps sustain glacial conditions in the past, rising CO2 may delay or disrupt the next natural cooling phase. But delay is not elimination. The orbital cycles persist. The tilt continues to vary. Precession continues its slow wobble. Eccentricity stretches and relaxes Earth's path around the sun. The astronomical metronome has not stopped. And the amplification mechanisms remain embedded in ice, ocean, and atmosphere. The freeze reshapes continents because the Earth system responds collectively once certain alignments occur. Small shifts begin the process. Feedback makes it vast. Survival adapts within it. And history unfolds in the narrow spaces between pulses. If ice ages are the dominant state of the last 2.5 million years, then our present warmth is not the norm. It is an interval, a pause. A thin band of relative stability suspended between long glacial chapters. The Holocene began about 11,700 years ago, at the end of the last major deglaciation. Temperatures rose rapidly. Ice sheets retreated northward. Sea levels climbed. Within a few thousand years, coastlines stabilized enough for ecosystems to settle into predictable patterns. That predictability changed everything. Agriculture emerged independently in several regions: the Fertile Crescent, China, Mesoamerica. Farming requires seasonal reliability. It depends on rainfall that follows patterns, winters that do not suddenly intensify, summers that allow crops to mature. The glacial world did not offer that reliability. The interglacial did. Stable coastlines allowed port cities to form. Predictable river systems enabled irrigation. Forest belts and grasslands remained within bounds long enough for permanent settlements to take root. Civilization is built on climatic calm. But the calm is geologically recent. When scientists compare the Holocene to previous interglacials preserved in ice cores, they find similarities: warm peaks lasting roughly 10 to 20,000 years, followed by gradual cooling back toward glacial conditions. Our current warm interval has lasted nearly 12,000 years already. Which raises a question. If past interglacials eventually ended, what prevents this one from doing the same? Orbital calculations show that northern summer insolation, a key factor in glaciation, has been gradually declining for several thousand years. Under purely natural conditions, this slow decline might eventually allow snow to persist longer at high latitudes. Given enough time, ice would begin to accumulate. But something unusual is happening. Carbon dioxide concentrations today exceed 420 parts per million, far higher than any level recorded in the last 800,000 years of ice core data. During previous interglacials, CO2 peaked near 280 to 300 parts per million before gradually declining. Today, instead of declining, it has risen sharply. If declining CO2 helps cool the planet into glaciation, rising CO2 may counteract orbital cooling. Some climate models suggest that anthropogenic greenhouse gas emissions could delay the next glacial inception by tens of thousands of years. In other words, human activity may be interfering with the natural rhythm. But interference does not mean mastery. The glacial clock is not a simple switch. It is a complex interaction between orbital forcing and internal feedbacks. While elevated CO2 could suppress ice growth under current orbital conditions, future orbital alignments might still favor cooling strongly enough to overcome greenhouse forcing, though not for many thousands of years. The timescales are vast, yet the sensitivity remains, and sensitivity cuts both ways. If the climate system amplifies small cooling nudges into glacial maxima, it can amplify warming nudges into rapid change as well. Feedback does not discriminate between directions. Ice albedo works in reverse during warming. As ice retreats, darker surfaces absorb more heat, accelerating further melt. Permafrost thaw releases greenhouse gases. Ocean warming reduces CO2 absorption. The same mechanisms that build ice sheets can accelerate warming. This is why understanding amplification is crucial. The central question has followed us from the beginning. If the trigger is small, why is the freeze so vast? Now the question acquires a mirror image. If amplification magnifies cooling, what happens when amplification magnifies warming? The Holocene has been stable not because the system is weak, but because forcing remained within certain bounds. Orbital variations unfolded gradually. Greenhouse gas concentrations moved slowly. We have altered that pace, and in doing so, we have inserted ourselves into a rhythm that long predates us. The glacial cycles shaped human evolution. They constrained migration. They carved landscapes that later civilizations would inhabit. Now, human influence may be reshaping the cycles. But whether we are postponing the next freeze or complicating the timing in ways we do not yet fully grasp remains uncertain. The orbital metronome continues. The The feedback machinery remains intact, and the warm window we inhabit is neither permanent nor guaranteed. It is simply the present phase of a much larger pulse. If we step back even further, beyond the last million years, the perspective becomes more unsettling. Ice ages are not permanent fixtures in Earth's history. For most of the planet's 4.5 billion-year existence, it has not been locked in repeated glacial cycles. The deep past includes long greenhouse periods when polar regions were ice-free and tropical climates extended toward higher latitudes. The glacial rhythm of the last 2.6 million years began relatively recently in geological terms. Why then? The answer reaches into tectonics. Over tens of millions of years, mountain ranges such as the Himalayas rose higher. Fresh rock exposed by uplift reacts chemically with atmospheric carbon dioxide through weathering. Rainwater binds with CO2 to form weak carbonic acid, which breaks down rock. The carbon is eventually transported to oceans and locked into sediments. This slow geological process gradually reduced atmospheric CO2 over millions of years. As CO2 declined, the planet cooled incrementally. Antarctica developed permanent ice sheets around 34 million years ago. Much later, Arctic ice became more stable. By the time the Quaternary began, background CO2 levels were low enough that orbital variations could tip the system into repeated glaciation. In other words, the orbital clock required a primed system. Without low baseline greenhouse gases, small changes in sunlight would not produce continental ice sheets. The system needed to sit near a threshold, and once near that threshold, feedback did the rest. This long cooling trend set the stage for the glacial cycles we now study. It created a climate system sensitive enough that slight orbital shifts could produce enormous outcomes. The freeze is vast not because the sun dims dramatically, but because Earth stands close to balance. Balance is deceptive. It can appear stable for thousands of years, but a balanced system requires only a modest push to lean one way or the other. Consider how small the orbital variations truly are. Eccentricity slightly alters the shape of Earth's orbit. Obliquity adjusts the tilt by only a few degrees. Precession shifts the timing of seasons relative to orbital position. None of these changes are violent. Yet, when aligned with low greenhouse gas concentrations and responsive feedbacks, they are sufficient to expand ice sheets across continents. Now consider our present condition. We are still within a glacial era, an icehouse world, because large ice sheets remain in Antarctica and Greenland. The long-term tectonic trend that lowered CO2 has not reversed. What has changed is the speed at which carbon is being added back into the atmosphere. In just a few centuries, human industry has elevated CO2 to levels unseen in nearly 1 million years. Geologically speaking, this is abrupt. If the Earth system amplifies gradual cooling, it may also amplify rapid warming. Ice albedo works both ways. Thawing permafrost releases methane. Warmer oceans hold less dissolved CO2. Feedback loops do not pause simply because the direction changes. This does not mean an immediate runaway scenario, but it does mean sensitivity remains. And sensitivity is the key to understanding the scale of glacial transformation. The central question still stands, unchanged. If the trigger is small, why is the freeze so vast? Because Earth's climate is not a rigid structure. It is a responsive network poised near thresholds. Orbital cycles provide gentle nudges. Geological conditions determine whether those nudges are amplified. For millions of years, declining CO2 made the planet increasingly vulnerable to glaciation. Once large ice sheets formed, they reshaped atmospheric and oceanic dynamics, reinforcing the cycle. The system learned its rhythm. Cold dominated. Warmth interrupted. Cold returned. We exist inside one of those interruptions. Whether human influence delays the next descent into ice or modifies the rhythm entirely remains uncertain. The timescales are long, the feedbacks are complex, but the machinery that once buried continents has not disappeared. It is embedded in the reflectivity of ice, in the chemistry of oceans, in the slow dance of Earth around the sun. The freeze is vast because the system amplifies, and amplification does not forget how to operate. If the glacial rhythm is driven by amplification, then the next question is not when the ice returns, but how it begins. Glaciation does not announce itself with a wall of white descending from the poles. It begins quietly. Snow lingers one summer longer than expected, then 2, then 10. Over centuries, the difference becomes measurable. Over millennia, it becomes decisive. The critical region is not the equator. It is high northern latitudes, especially around 65 degrees north. Here, summer sunlight determines whether winter snow melts completely or persists. If summers grow just cool enough that snow survives year after year, ice sheets can begin forming. It is not winter severity that matters most. It is summer weakness. This is the subtlety of orbital forcing. A slight reduction in summer insolation in northern latitudes does not plunge the globe instantly into deep freeze. It simply alters the seasonal balance. But seasonal balance accumulates. Persistent snow becomes compacted firn. Firn becomes glacial ice. Glacial ice spreads outward, flowing under its own weight. As the ice sheet thickens, it begins reshaping the landscape beneath it. And as it spreads, the planet brightens. More reflection means less absorbed heat. Less absorbed heat means cooler summers. The feedback strengthens. At first, only regional cooling occurs, but ice sheets influence atmospheric circulation. Cold air masses expand. Storm tracks shift southward. Dryness increases across some mid-latitude regions as moisture becomes locked in frozen reservoirs. Meanwhile, sea levels begin to fall. As ice accumulates on land, water is removed from the oceans. Coastlines extend outward. Continental shelves emerge. What was once shallow sea becomes exposed land. Over thousands of years, this reshapes geography. But the process remains slow. The glacial buildup phase can last tens of thousands of years. Ice sheets creep forward inch by inch, century by century. The change is imperceptible within a human lifetime, yet relentless across generations. Then comes the paradox. The collapse of ice ages is often faster than their growth. As orbital configurations shift and summer insolation increases, melting begins. Initially modest, the melt exposes darker ground beneath. Darker surfaces absorb more heat. Absorbed heat accelerates melting. Fresh water flows into oceans. Atmospheric CO2 rises as oceans warm and release dissolved carbon. Feedback reverses direction. Deglaciation can proceed rapidly relative to glacial buildup. Within several thousand years, sometimes even less, massive ice sheets retreat dramatically. Sea levels rise. Climate zones shift northward. Ecosystems reorganize. The system behaves asymmetrically. Slow accumulation, faster release. Why? Because thresholds operate differently in each direction. During glaciation, snow must survive many summers to build thickness. But once melting dominates, the loss of reflectivity accelerates collapse. The feedback loop that once amplified cooling now amplifies warming. This dynamic reinforces the central tension. The orbital trigger is modest. The amplification is immense. And once large ice sheets exist, they create their own inertia. Thick ice resists melting. It responds sluggishly to small warming trends. But when warming surpasses a critical level, collapse accelerates. This interplay between inertia and threshold defines the glacial cycle, yet the deeper mystery still hovers. Why did the dominant pacing shift to 100,000 years when eccentricity, the weakest orbital signal, governs that timescale? One emerging idea is that eccentricity does not act alone. It modulates the strength of precession, influencing seasonal contrasts more strongly during certain alignments. When ice sheets grow large enough, they may respond primarily to these amplified alignments rather than to tilt alone. In this sense, the 100,000-year cycle may represent synchronization, a resonance between orbital variations and internal feedback strength. The weakest beat becomes dominant not because it is powerful alone, but because it aligns the system at critical moments. This is not a simple pendulum. It is a layered resonance system. And resonance, once established, can persist for hundreds of thousands of years. The freeze, therefore, is vast not because the sun changes dramatically, but because Earth's internal machinery is tuned to respond when certain alignments occur. We live during a warm alignment, but alignments change, and the clock continues to turn. To understand why the 100,000-year rhythm dominates, we have to think less like observers of weather and more like engineers studying a complex machine. Imagine a system composed of multiple components, each responding on different timescales. The atmosphere reacts quickly, years to decades. The surface ocean adjusts over decades to centuries. The deep ocean integrates heat over centuries to millennia. Ice sheets respond over thousands of years. The solid Earth rebounds over tens of thousands. Now introduce orbital variations, subtle but persistent. Each component interprets that variation differently. The atmosphere feels seasonal contrast immediately. The ocean absorbs and redistributes heat slowly. Ice sheets accumulate mass only if summers repeatedly fail to melt winter snowfall. This mismatch in response times creates layering. Short cycles, like precession, may influence seasonal extremes, but average out over longer spans if the ice sheets are too massive to respond quickly. The 41,000-year tilt cycle may drive early glaciations when ice sheets are smaller and more flexible. But once ice grows thick and continental in scale, its inertia increases. Inertia favors longer cycles. A massive ice sheet does not melt simply because one orbital alignment produces slightly warmer summers. It may require sustained forcing across multiple alignments. The 100,000-year eccentricity cycle, though weak in direct energy terms, creates envelopes of stronger seasonal contrast when combined with precession. During those alignments, the cumulative effect may finally overcome ice inertia. In this framework, eccentricity acts less as a direct cause and more as a gatekeeper, modulating when other cycles are strong enough to produce large-scale transitions. The climate system becomes synchronized with the longer rhythm because the ice sheets themselves have grown too stable to respond to shorter pulses. This may explain why the dominant pacing shifted about 1 million years ago. As baseline global temperatures cooled and ice sheets became more extensive, the system reorganized. What once responded primarily to tilt began responding to longer envelopes of forcing. The weakest astronomical signal became dominant because the system evolved to prefer it. But this explanation is still incomplete. Deep ocean circulation adds another layer of complexity. The ocean stores heat that can delay surface responses by centuries or longer. If deep water formation patterns shift during glacial growth, they can lock away heat for extended periods. Releasing that heat later can accelerate deglaciation. Carbon cycling adds further delay. CO2 does not move instantly between atmosphere, ocean, and biosphere. Its redistribution unfolds gradually. When ice sheets expand and oceans cool, carbon is drawn downward. When warming begins, CO2 is released, strengthening the greenhouse effect and accelerating melt. These delays create hysteresis, a situation where the path into glaciation differs from the path out. The system remembers its past state, and memory contributes to magnitude. If ice sheets are large, they reinforce cooling even when orbital forcing begins to weaken. Conversely, when ice shrinks, warming accelerates even if forcing stabilizes. This is why small orbital variations can lead to enormous changes. The system is not linear, it is state-dependent. A small nudge applied to a stable system may produce little change. The same nudge applied to a system near threshold can produce transformation. Which brings us back, again, to the persistent question. If the trigger is small, why is the freeze so vast? Because magnitude is not about the size of the push. It is about the sensitivity of the system being pushed. Earth's climate during the Quaternary sits near critical balance. Low baseline CO2, existing polar ice, and responsive feedback loops create conditions where modest orbital shifts can reorganize the planet. The freeze is vast because the system amplifies alignment. And that amplification is not accidental. It is embedded in the structure of ice reflectivity, carbon chemistry, ocean heat storage, and atmospheric circulation. The clock continues, not loudly, not violently, but persistently. And when alignment and amplification meet, continents change. By now, the machinery of ice ages appears almost mechanical. Orbital shifts adjust sunlight. Ice albedo amplifies cooling. Oceans absorb carbon. Feedback locks the planet into cold. Inertia favors long cycles. Deglaciation releases energy quickly. But there is a deeper layer beneath mechanics. Human perception. For most of our species' existence, climate was not an abstract system measured in isotopes and orbital parameters. It was immediate, tangible, felt in the body. Cold meant hunger. Unpredictable seasons meant migration. The glacial world shaped not only landscapes but psychology. Consider early Homo sapiens emerging roughly 300,000 years ago. Our species evolved during a period of strong glacial cycling. Entire generations were born into climates that shifted within their lifetimes. Regions that were once grasslands became arid, river systems dried or expanded. Animal migrations changed course. Adaptation was not optional. Mobility became strategy. Social cohesion became survival. Groups that could share resources, transmit knowledge, and adjust rapidly were more likely to endure instability. The freeze did not just sculpt valleys, it sculpted behavior. When ice sheets advanced, populations retreated toward refugia. When warming opened corridors, migration expanded. Genetic evidence reveals repeated bottlenecks, moments when human populations shrank dramatically before expanding again. Climate pressure filtered lineages. And yet, our cognitive architecture evolved in response to short-term threats. Storms, predators, droughts, not 100,000-year rhythms. This mismatch matters. The glacial clock operates on scales beyond instinct. No human mind can intuitively grasp a 100,000-year cycle. We respond to what we see, not what unfolds slowly over millennia. This psychological limitation shapes modern perception. We assume stability because we were born into it. The Holocene has been comparatively calm for 12,000 years, enough time for agriculture, cities, and global networks to develop. To us, this feels normal. But normal, in geological terms, is cold. Most of the last million years were glacial. Warmth is interruption. This inversion challenges perception. We treat the freeze as anomaly because we inhabit a warm window. In reality, the ice is the dominant state of the recent Earth. And the rhythm persists. Orbital calculations show that the next glacial inception, under natural conditions, would not occur for tens of thousands of years due to current orbital geometry. Northern summers are not yet weak enough to allow persistent snow accumulation. But that calculation assumes a natural carbon baseline. We have altered that baseline. Rising greenhouse gas concentrations complicate the forecast. Elevated CO2 increases global temperatures, potentially suppressing glacial growth even when orbital conditions favor cooling. In effect, human activity may have inserted a new variable into a very old rhythm. But psychological perception often reduces this to a binary narrative: warming versus cooling, natural versus human. The deeper reality is more complex. The glacial system is not a switch. It is a layered oscillator influenced by astronomical cycles and internal feedbacks. Human forcing interacts with that oscillator, potentially shifting timing without eliminating the underlying mechanics. And because the cycles unfold slowly, their reemergence would be gradual. There would be no dramatic announcement. Only slightly cooler summers at high latitudes, slightly longer snow persistence, incremental expansion of seasonal ice. The early stages would be almost invisible within a human lifetime, which returns us, again, to the central question. If the trigger is small, why is the freeze so vast? The answer lies not only in physics, but in perception. Small triggers matter because they accumulate, because feedback amplifies them, because systems near thresholds respond disproportionately. But we are poorly equipped to sense accumulation when it unfolds across centuries. Our instincts evolved for immediacy. The glacial clock does not operate on instinctual timescales. It operates patiently. And patience, when amplified by feedback, reshapes continents. There is another psychological layer to this story, one that extends beyond ancient survival and into modern confidence. For 12,000 years, the Holocene has behaved with remarkable restraint. Temperature fluctuations have been relatively modest. Sea levels stabilized after the great post-glacial rise. Agricultural cycles settled into predictable ranges. That stability allowed planning. Planning allowed surplus. Surplus allowed specialization, architecture, trade, and eventually global civilization. Over time, stability became expectation. We design infrastructure assuming coastlines will not migrate dramatically within centuries. We construct cities near rivers assuming seasonal flow will remain within tolerable limits. We build global supply chains that depend on predictable weather patterns. We have internalized stability as default. But geological memory contradicts that instinct. Ice cores reveal that climate systems can reorganize abruptly when thresholds are crossed. The glacial world was punctuated by rapid shifts. Ocean circulation slowed and restarted. Carbon moved between reservoirs. Ice surged and retreated in pulses. The stability we depend on is not guaranteed by design. It is the product of alignment, orbital geometry, greenhouse gas concentration, ocean circulation patterns, all currently arranged in a configuration that favors warmth. Alignment changes. This is where fragility enters the narrative. Fragility is not weakness, it is sensitivity. A fragile system is one that responds strongly to perturbation. The quaternary climate system is fragile because it sits near the balance point between icehouse and interglacial states. That fragility produced vast ice sheets from small orbital shifts. It can also produce rapid warming from elevated greenhouse gases. The same amplification mechanisms operate regardless of direction. Yet psychologically, humans tend to frame climate as either stable or broken, either natural or disrupted. The reality is that the system has always been dynamic. What is new is the rate of forcing. Orbital variations unfold slowly and predictably. Carbon emissions have risen sharply within centuries. The pace of change influences how feedback unfolds. Some feedbacks require time to activate fully. Ice sheet growth, for example, requires persistent cooling over millennia, but ice retreat can respond more quickly to warming. This asymmetry matters. If orbital cooling were to begin in a future with high atmospheric CO2, the greenhouse effect might counterbalance early snow persistence. But if CO2 concentrations eventually decline, whether naturally or through deliberate intervention, orbital cycles would still be waiting. The glacial clock has patience, which leads back to the central thread that runs beneath every chapter. If the trigger is small, Why is the freeze so vast? Because the system does not require a large shove to reorganize. It requires sustained imbalance. Small changes, when persistent, reshape feedback loops. Feedback loops reshape global climate, and the magnitude becomes continental. Human civilization has flourished within a narrow band of climatic variability, but that band exists within a much larger oscillation. Understanding that oscillation is not about predicting a date for the next ice age. It is about recognizing scale. Scale of time, scale of amplification, scale of fragility. The glacial rhythm is not an anomaly in Earth's history. It is a recurring chapter. We are not outside the system. We are inside it. Inside a warm intermission between freezes. And the system that once buried continents beneath ice has not disappeared. It is simply paused. If the freeze is vast because amplification magnifies subtle orbital shifts, then the final layer of the puzzle is timing. Not whether ice returns, but when. Orbital calculations can project Earth's geometry tens of thousands of years into the future with remarkable precision. The tilt of the axis, the wobble of precession, the stretching of eccentricity, all follow gravitational laws governed primarily by interactions with Jupiter and Saturn. In that sense, the astronomical clock is predictable. According to current orbital configuration, northern summer insolation is not declining sharply enough to trigger immediate glacial inception. In fact, eccentricity is presently relatively low, which reduces the strength of precession-driven seasonal contrasts. Under natural carbon levels similar to pre-industrial conditions, the next glacial inception might have begun tens of thousands of years from now, perhaps 50,000 years in the future. But that estimate assumes a baseline atmosphere similar to previous interglacials. It assumes CO2 would gradually decline over millennia, allowing cooling to accumulate. Instead, atmospheric carbon has risen rapidly. Higher greenhouse gas concentrations increase global temperature and reduce the likelihood that snow in high northern latitudes will persist summer after summer. Persistent snow is the seed of ice sheets. Without that seed, glaciation cannot begin. Some climate simulations suggest that elevated CO2 may delay the next glacial cycle substantially, perhaps by tens of thousands of years. In effect, human influence may have overridden the early stages of natural cooling. But delay is not cancellation. Orbital forcing continues. Eventually, configurations will arise that strongly reduce northern summer insolation. If greenhouse gas concentrations decline sufficiently by that time, the conditions for glaciation could reappear. The clock does not forget. This perspective reframes the question. We often ask whether human activity is causing warming, but in the context of glacial cycles, a parallel question emerges. Are we postponing the next freeze? And if so, what does postponement mean within a system designed to oscillate? A delay of tens of thousands of years is enormous in human terms, far longer than recorded history. But it is brief in geological time. The Quaternary period spans millions of years. The glacial rhythm has repeated dozens of times. A postponed cycle remains part of a larger oscillation. The deeper issue is not simply timing. It is sensitivity. If small orbital shifts can eventually produce mile-thick ice sheets, then the system remains capable of dramatic transformation. Whether cooling or warming dominates at any moment depends on alignment between external forcing and internal feedback. We are currently amplifying warming through greenhouse gas emissions, but the underlying mechanics that produce glaciation remain embedded in Earth's structure. Ice still reflects sunlight. Oceans still absorb carbon. Orbital variations still modulate insolation. The amplification engine is still assembled. Which leads us back once more to the core question that has threaded through this entire narrative. If the trigger is small, Why is the freeze so vast? Because magnitude emerges from persistence. Because subtle changes sustained over thousands of years accumulate into thresholds. Because once feedback aligns, scale multiplies. The freeze is not explosive, it is cumulative, and cumulative systems are patient. Our civilization measures time in decades and centuries. The glacial clock measures time in tens of thousands of years. Both clocks are ticking, but only one has already reshaped continents repeatedly. If we imagine the Earth as it might appear at the beginning of a future glacial cycle, the change would not be cinematic. There would be no sudden wall of ice crossing continents in a generation. The early signs would be almost invisible. Summers at high northern latitudes would become slightly cooler. Snowpack would persist a little longer into the warm season. The difference from one year to the next would be negligible. Only when measured across centuries would the pattern emerge. But persistence is everything. A snowfield that survives one summer is fragile. A snowfield that survives 100 consecutive summers begins to compact into ice. Ice thickens slowly. Its surface rises. Higher elevation cools the air above it further, reinforcing preservation. The system builds upon itself. As ice expands, sea levels would begin to fall gradually. Not dramatically at first, perhaps centimeters per century. Coastlines would shift almost imperceptibly, but over millennia, the cumulative drop would expose continental shelves. River systems would adjust to new gradients. Ecosystems would migrate. Civilization, if it still existed in recognizable form, would confront a creeping transformation rather than a single event. Agricultural zones would slowly drift equatorward. Northern regions would shorten their growing seasons. Infrastructure designed for Holocene stability would face incremental stress. But here's the paradox. Glaciation is slow enough to allow adaptation, until feedback accelerates. Once ice sheets reach sufficient size, atmospheric circulation reorganizes more dramatically. Storm tracks move, precipitation belts shift, cooling intensifies beyond local effects. At that point, what was gradual becomes systemic. This dynamic, slow build, amplified response, mirrors the past. Yet our present is different in one crucial respect. Greenhouse gas concentrations remain elevated. Even if emissions stopped today, carbon already in the atmosphere would persist for centuries. The thermal inertia of the oceans would continue to influence climate for long spans. If a natural cooling phase began while CO2 remained high, the greenhouse effect might counterbalance early ice growth. The system would hesitate. But orbital forcing does not cease. Eventually, alignments may become strong enough to overcome even elevated greenhouse baselines, though that scenario lies far beyond foreseeable human timelines. This interplay reveals something profound. The glacial cycle is not a single switch between cold and warm. It is a negotiation between forcing and feedback, between persistence and threshold. The freeze becomes vast not because the sun dims significantly, but because the Earth system integrates small imbalances over immense spans of time. Integration creates inevitability, and inevitability does not feel dramatic while it unfolds. For those living 20,000 years before the last glacial maximum, the approach of peak ice likely felt gradual. Only in retrospect does the scale appear monumental. From space, the Earth during glacial maxima looks transformed, white dominating the northern hemisphere. But from ground level, the change was generational. This perspective reframes fear. The next freeze, if it comes naturally, would not surprise overnight. It would reveal itself slowly, as patterns in snow persistence, sea level trends, vegetation shifts. And yet, even slow change accumulates into continental transformation, which returns, quietly and persistently, to the central question. If the trigger is small, why is the freeze so vast? Because vastness is not about speed. It is about accumulation amplified by feedback. The glacial clock does not need drama. It needs time. And time, combined with sensitivity, reshapes worlds. After tracing the machinery, the feedback loops, the orbital rhythms, we return to the central question, not as speculation but as synthesis. If the trigger is small, why is the freeze so vast? One hypothesis places emphasis on orbital resonance. The 100,000-year eccentricity cycle, though weak in total energy change, modulates the intensity of precession. When eccentricity is high, seasonal contrasts become more extreme in certain hemispheres. When aligned properly, northern summers weaken enough, repeatedly, to allow ice sheets to grow beyond recovery thresholds. In this view, eccentricity does not act alone. It times the moments when shorter cycles combine constructively. Another hypothesis focuses on ice sheet dynamics themselves. As ice sheets grow larger, they alter their own stability. Thick ice depresses the crust, lowering elevation at the margins and affecting temperature gradients. The deeper the depression, the more the ice becomes locked into cold conditions. Once a critical mass is reached, melting requires sustained and amplified forcing. This introduces inertia as a dominant factor. A third hypothesis emphasizes carbon feedback thresholds. During glaciation, atmospheric CO2 declines gradually. But perhaps once CO2 drops below a certain concentration, the climate system enters a regime where ice growth becomes self-sustaining until a much stronger orbital configuration forces reversal. In this scenario, the 100,000-year cycle reflects carbon thresholds interacting with orbital pacing. There is also the ocean. Deep ocean circulation operates as a long-term integrator of heat and carbon. If circulation reorganizes during glacial buildup, it may sequester heat and carbon in ways that delay deglaciation until certain orbital alignments restore strong overturning. The delay aligns the collapse of ice sheets with the longer eccentricity cycle. Each hypothesis explains part of the pattern. None explains all of it. The truth may not lie in a single mechanism, but in their interaction. Resonance between orbital geometry, ice sheet inertia, carbon chemistry, and ocean circulation. A layered oscillator. And oscillators behave differently depending on state. Small pushes at the right moment produce large swings. Small pushes at the wrong moment produce almost nothing. Which suggests that magnitude is not simply about force, it is about timing. The freeze becomes vast when forcing and feedback synchronize. When they do not, the system remains in relative equilibrium. This perspective reframes the glacial cycle as neither purely astronomical nor purely terrestrial. It is hybrid. The sun provides rhythm, the earth provides amplification, and synchronization between them determines scale. But uncertainty remains. Despite decades of modeling, drilling, and analysis, no theory reproduces every feature of the 100,000-year cycles perfectly. Some glacial terminations occur slightly earlier or later than expected from orbital forcing alone. Some warm periods are longer or shorter than models predict. The system retains elements of unpredictability, which returns us to humility. We understand much more than 19th-century scientists who first mapped glacial scars. We can calculate orbital variations hundreds of thousands of years forward and backward. We can measure ancient CO2 directly from ice bubbles. Yet the full choreography of the freeze is not completely resolved. And perhaps that is fitting, because the scale of the system exceeds human experience. The glacial clock is not designed for our comprehension. It operates whether or not we understand it fully. But the pattern is undeniable. Cold dominates. Warmth interrupts. Cold returns. And the amplification that transforms subtle orbital shifts into continental ice remains embedded within the Earth system. The question, then, is not whether the freeze is possible. It is whether alignment will occur again. And if it does, what kind of world will be waiting to experience it? If alignment is the key, then the future of the glacial rhythm depends on how external forcing and internal sensitivity interact over immense spans of time. Under purely natural conditions, orbital geometry would continue its slow evolution. Eccentricity would wax and wane, tilt would oscillate, precession would shift the timing of seasons relative to perihelion and aphelion. At some distant point, perhaps tens of thousands of years from now, northern summers would weaken sufficiently to allow persistent snow accumulation. But the system no longer operates under purely natural conditions. Anthropogenic greenhouse gases have altered the radiative balance of the planet in ways that previous interglacials did not experience. Elevated CO2 increases baseline temperatures and reduces the likelihood that summer snow at high latitudes will survive long enough to seed ice sheets. In effect, greenhouse forcing may have shifted the threshold. If glacial inception depends on sustained summer cooling and low atmospheric CO2, then higher CO2 concentrations raise the bar. Orbital alignment alone may not be enough under current atmospheric conditions. Some modeling studies suggest that with sufficiently elevated CO2, glacial inception could be delayed for 50,000 years or more. That delay would represent a significant disruption to the natural pacing of the last million years. But delay does not imply permanent immunity. Orbital cycles operate over hundreds of thousands of years. Carbon cycles operate over similar magnitudes when geological processes dominate. If human emissions eventually stabilize or decline, atmospheric CO2 could slowly decrease over millennia through natural sequestration in oceans and sediments. When that happens, if it happens, orbital forcing will still be there, waiting. The system remains capable of amplification. This interplay introduces a new layer of complexity into the glacial narrative. For most of the Quaternary, the rhythm was governed by slow astronomical and geological processes. Now, a species has introduced rapid forcing into the equation. The glacial clock may be postponed. It may be distorted. It may even temporarily flatten. But the structural sensitivity of the Earth system remains. Ice still reflects sunlight. Oceans still absorb carbon. Deep water still circulates heat. Thresholds still exist, which leads back, for the final time, to the central question that has carried us through this exploration. If the trigger is small, why is the freeze so vast? Because vastness is born from interaction. Because subtle, sustained imbalances accumulate into state changes. Because feedback transforms modest forcing into planetary transformation. The freeze is not dramatic at its beginning. It is dramatic in its consequence. And consequence depends on alignment. We live in a warm alignment, an interglacial sustained by current orbital geometry and amplified by elevated greenhouse gases. But alignment shifts. The orbital metronome continues, and the Earth system retains its capacity for transformation. Whether the next major shift lies tens of thousands of years away or is delayed far beyond that is less important than understanding the mechanism itself. The glacial cycle is not a relic of the past. It is an expression of how sensitive planetary systems behave near thresholds. Cold is not ancient myth. It is recent history. And the machinery that produced it is still intact. We remain inside the oscillation, not outside it, the tween pulses, between extremes, inside a brief, warm chapter of a much longer story. If we step outside the technical language, outside eccentricity, obliquity, carbon feedbacks, ocean circulation, what remains is something far more elemental. Earth breathes, not in minutes, not in seasons, but in pulses of ice and warmth that span tens of thousands of years. For most of the last million years, the breath has been long and cold. Ice dominates. Then, briefly, the planet exhales into warmth. Forests expand, seas rise, life reorganizes. Then the inhalation begins again. Cold is not an interruption in Earth's story. Warmth is. This perspective changes scale. We often imagine ourselves at the center of climate history, debating warming trends, projecting centuries ahead. But in geological time, centuries are flickers. Even millennia are brief. The glacial pulse measures time differently, and within that pulse, humanity has existed for only a fraction of a single cycle. Our entire recorded history fits inside the final sliver of the most recent warm interval. Cities, empires, technology, all emerged within conditions that were unusually stable. That stability feels permanent because it has lasted longer than any human memory. But it is not permanent. The orbital clock continues, indifferent to civilization. The tilt shifts. The wobble progresses. The orbit stretches and relaxes. Jupiter and Saturn exert their gravitational influence whether we observe it or not. The machinery does not pause for us. Yet this is not a fatalistic story. The freeze does not descend like an asteroid impact. It does not arrive as sudden annihilation. It builds gradually. It accumulates. It requires alignment, which means awareness matters. Understanding the system does not grant control over orbital cycles, but it does grant perspective. Perspective that small shifts, sustained, can lead to continental transformation. Perspective that amplification defines scale. Perspective that stability is conditional, not guaranteed. The freeze becomes vast not because it is violent at the start, but because it is patient. Patience is the defining trait of planetary systems, and patience reshapes worlds. From space, the difference between glacial maximum and interglacial warmth is dramatic. White blankets of ice extending across hemispheres, sea levels lower, deserts wider. Then warmth returns, and blue oceans reclaim continental margins. Both states are natural. Both are chapters in the same oscillation. We live in the warm chapter. That warmth allowed agriculture to flourish. It allowed coastlines to stabilize. It allowed humans to construct networks of trade and knowledge. But warmth is not the default of the recent Earth. It is the intermission. The central question that began this journey still echoes. If the trigger is small, why is the freeze so vast? Because Earth is sensitive. Because feedback magnifies persistence. Because thresholds transform accumulation into magnitude. And because time, immense time, allows subtle forces to become geological events. The glacial rhythm is not myth. It is measurable. It is recorded in ice bubbles, ocean sediments, carved valleys, and rebounding crust. It is part of the architecture of the planet we inhabit. We are not separate from that architecture. We are a brief phenomenon within it, living in a warm window, between breaths. If there is a final image to hold, it is not one of catastrophe. It is one of scale. Imagine Earth from deep space during a glacial maximum. The northern hemisphere glows white. Ice sheets stretch from pole to mid-latitudes. Sea levels are lower. Coastlines extend outward. Winds carry dust across exposed plains. The planet appears austere, restrained, quieter. Now imagine the same planet during an interglacial like today. Ice retreats to the poles. Forests spread northward. Oceans swell against continental margins. Cities shine at night. A thin electric lattice across the surface. Both versions are Earth. Both are expressions of the same system. The difference between them began with something subtle, a slight weakening of summer sunlight in northern latitudes, sustained over thousands of years. A small imbalance that persisted. Feedback amplified it. Ice expanded, carbon shifted, oceans cooled, vastness emerged from persistence. And when alignment reversed, when feedback tipped the other way, warmth returned. The glacial clock is not dramatic because it is sudden. It is dramatic because it is cumulative. We tend to measure significance by immediacy, storms, earthquakes, eruptions, but the freeze does not operate that way. It accumulates quietly until continents are transformed. This reframes the meaning of scale. A system can appear stable within a human lifetime while moving steadily toward a different state across millennia. The early stages are almost invisible. Only in retrospect does the magnitude become clear. The same was true for past glacial maxima. No generation experienced the full descent into peak ice. Each generation simply lived within slightly cooler summers, slightly expanding snowfields. Only deep time reveals the full arc, and deep time is indifferent. The orbital cycles that modulate sunlight will continue for millions of years. The tectonic forces that regulate long-term carbon balance will persist. Ice sheets will advance and retreat again and again under the right conditions. The freeze is vast because the Earth system allows it to be, because it is structured to respond collectively when alignment occurs, because feedback multiplies small signals into continental consequence, and because time is generous. We inhabit a narrow band of warmth carved out between these pulses. That warmth enabled language, culture, architecture, exploration. It allowed us to ask questions about the sky and the ice beneath our feet. It allowed us to uncover the clock. But uncovering the clock does not stop it. The central question that began this journey does not resolve into a single equation. It resolves into understanding. If the trigger is small, why is the freeze so vast? Because Earth is not rigid, because it sits near balance, because subtle, sustained changes accumulate until they cross thresholds, and because once crossed, feedback carries the rest. The ice will return someday, not as an anomaly, but as a continuation of rhythm, perhaps not in any time that touches human memory, perhaps long after our cities have changed form, but the rhythm is older than civilization and will outlast it. We are living in the warm interval, between inhales, between exhalations, between pulses of a planet that breathes in ice and releases in warmth. And the breath continues.